I'm going to get going, and thank you for joining us. Thank you very much to the organizers for having organized this conference during what has been a very difficult and trying time for all of us. I'm going to get rolling right away because there's a lot to cover, and I'm going to begin with a review of the basic modal logic of time, nothing particularly controversial here. A definition of earlier than, we could of course define later than, but we're going to define before in terms of causation. E is before F if E causes F and not F causes E. Of course, at some point, we're going to have to say possibly E causes F and not possibly F causes E. But for the purposes of today's talk, we're not going to introduce those extra modal predicates. From this definition, it obviously follows that if E is before F, then it's not the case that F is before E. What is before cannot be later. But it's not the case that from E before F, we can infer that F before E. In words, what is not later need not be before. And furthermore, if causes is transitive, well, then before is transitive as well. So E before F and F before G entails that E is before G. So that gives us, you might say, the notion of a chain of causes and therefore of a timeline. Well, from the fact that what is not later need not be before, it follows that possibly neither E is before F and not F is before E. So something can be neither later nor before something else. And that's going to yield two possibilities for the concept neither later nor before. The first of these is E causes F and F causes E, and the second is not E causes F and not F causes E. And of course, the first of these is going to end up being Newtonian simultaneity, and the second one is going to end up being the light cone, which, as you know, has two parts. One of the parts is the geometrical part, and one of the parts is the causal part. And this causal part, as all of us know, has been an irritant from the very beginning. So let me give you an example of what I mean by an irritant by contrasting two quotes by John Norton here. John Norton, I mean, to be clear, from my generation, member of the golden age of Pittsburgh, if I'm citing his work, not to criticize him, but because for my generation, he's one of the leading people on Einstein. And if we can see this tension in Norton, then I think that's telling us that we'll see it elsewhere, and we do see it elsewhere when we talk to physicists. So here is Norton talking about the light cone. Light cone structure, since the speed of light is generally taken to be the fastest, that causes can propagate their effects. Once we know how the light cones are distributed in space, we can say a great deal about what is possible and impossible causally. So this is of great interest to us. It's called the light cone. Recent paper on causality, causation as folk science. My purpose in this paper is to take issue with this view of causation. I urge that the concepts of cause and effect are not the fundamental concepts of our science, and that science is not governed by a law of principle of causality. Such a plastic notion fails to restrict possibility and is physically empty. So it's a bit strange because on the one hand, this concept of causation is, key to something which is of great interest to us. And on the other hand, it is a plastic notion that fails to restrict possibilities entirely. And again, to reiterate, the reason I'm bringing this up is not to mock anyone, but because I think this tension is pretty widely distributed, and anyone who's taught courses where the light cone is explained has that anxiety the whole time that they're teaching it. So what is the source of this irritant? What is historically the source of this irritant, but what is also systematically the source of this irritant? And the short answer, I think, is simply that the light cone is a fusion of Newton's and Leibniz's theories of time. And so the antipathy between these two gentlemen is, you might say, worked into the light cone from the very beginning. On the one hand, we have Newton. Time is a one-dimensional manifold that differs from space in that its parts are successive and not simultaneous, versus Leibniz. Time is a causal structure and has no existence independently of causal relations. We would say that it supervenes on causal relations. So according to Leibniz, events sort themselves into slices of what he calls compossibles or compatibles, which slices are inconsistent but connected. So here is Leibniz, mais pour parler plus juste, l'étendue est l'ordre des coexistences possibles, comme le temps est l'ordre des possibilités inconsistantes, mais qui ont pourtant une connexion, right? So extension is the order of possible coexistence. Time is the order of inconsistent possibles, which are nevertheless connected. Furthermore, these orders frame not only what is actually the case, but what could have been in their place, just as numbers are indifferent to what they number. So they're actually possibility slots, you might say. So I'm going to say quite a bit today about how this fusion of Leibniz and Newton actually occurred. But let me highlight a few points about Leibniz's theory, because they're going to come back later on in the talk. So firstly, from our point of view, it's a local theory. Sets of coexistence corresponding to Newton's space are logically compatible, but unlike the inconsistent possibilities that determine temporal order, they're not connected by actions at a distance. Secondly, space and time in Leibniz's theory are intrinsically connected to his theory of possible worlds, which is the source of many of the modern logical methods that I'm using with some of my grad students in more systematic work on this topic. In particular, Leibniz links the two properties just discussed, compatibility and incompatibility with necessary connection, to notions of logical entailment and thus to information. So two events E and C are compatible if neither logically entails the other or its negation, right? Two events E and C are incompatible if and only if either logically entails the negation of the other. Finally, incompatible events are successive if, despite what we just said about their being incompatible, one of them is in fact the cause of the other. So spatial simultaneity and successivity are linked to logico-epistemological properties, which we might say analogize order dependence or independence. The order in which I assess simultaneous events has no informational consequences, whereas the order in which I assess successive events does. And we're going to see both of these properties reappear when we talk about the work of Dirac later, assuming that we get to the work of Dirac. Third point, Leibniz's theory involves two important principles. Firstly, the principle of sufficient reason, which is later called the law of causality, and a symmetry principle known as the principle of the identity of indiscernibles, which most of you are probably familiar with. If X and Y have all of their properties in common, then X is identical to Y. So these Leibnizian principles are combined already by Leibniz to produce a form of symmetry argument that characterizes German mathematics and physics right up until the work of Helmholtz, Klein, Einstein, and Weil. To speak quite loosely, to cover all the possible cases, if a theoretical entity disappears under transformations that correspond to a symmetry, that entity is unreal and the theory should be reformulated in such a way as to eliminate it. And as most of you know, Leibniz immediately applied this reasoning to time itself. Since the laws of impact are time reversible, the direction of time is unreal. Now, this work of Leibniz's was immediately extended by mathematicians and physicists and philosophers associated with two academies, the first of which was in Berlin, founded by Leibniz, later led by Euler. It's still there, as you know. The second in St. Petersburg was founded by Euler himself. And when he left Berlin to return to St. Petersburg, he picked his successor in Berlin, who was Louis Lagrange. So most of the physicists and mathematicians that I'm going to be talking about today belong to this academy, which still exists. And one of those people, of course, was Immanuel Kant, the hero of our conference, who was already quite well known at the time, for his work in cosmology and the nebular hypothesis. All right, so a lot of this has been forgotten over the last 150 years. A lot of it is coming back now. We have people who are doing some very interesting work on these academies. But for the most part, the details that I'm going to be taking you into today have pretty much vanished from the literature to the best of my knowledge. So the first thing I'm going to do is to look at Kant's frame theoretical derivation of the kinematic parallelogram law, which we see is a careful inversion of a proof that we find in Euler. And I'm not going to go into the technical details of this construction as much today as I have in previous versions of this talk, simply because it's now all been published in Kant-Studien. The name of the paper is Kant on Time 1, the Kinematics of the Metaphysical Foundations of Natural Science. This was the first step in what became the Erlangen program. So from our point of view, Kant's theory is a relativistic theory of space-time with absolute simultaneity, which is sometimes referred to as neo-Newtonian space-time. And I'm then going to take that approach of Kant's, and I'm going to show how it's extended in the work of Einstein's. And to be clear here at the outset, the purpose of this talk is not to say Einstein stole or took this thing from Kant, right? We're describing a large mainstream tradition. Many of the participants in this tradition work on the same problems, whether or not they're particularly conscious of the work of their immediate predecessors. But essentially, Einstein's 1905 parallelogram law proof uses the same method as Kant's, but of course with this absolutely world historical difference, which is the changing of the definition of simultaneity being used. Because Kant had consciously argued against Leibniz by introducing instantaneous causal connections between the compossible events in a spatial slice. So that's just not in Leibniz's theory, at least as near as I can tell. In that sense, Kant defines simultaneity by means of instantaneous actions at a distance, although in Kant's theory, of course, both of these elements are present, right? The mathematical theory of time, transcendental aesthetic, the causal theory of time, the analogies of experience. So Einstein's 1905 definition of simultaneity uses causal signals with finite speed, that is to say local signals, local actions. But aside from that, the proof methods are the same. So the primary source for this first bit, which is on the kinematic parallelogram law, is, aside from Kant's work, Euler's 1736 Analytical Mechanics, which is pretty much the book that kicks off what I call the Euler-Lagrange research program, which culminates in 1788 with the Mécanique analytique, published in Paris, but most of this work was done at the BBAW. And there's a twin academy in St. Petersburg, also led by Euler, and lots of the names of the people in these academies. I don't have to go into that. So Kant owns a copy of this book, and in fact, in 1746, when he's merely in his 20s, he sends a copy of his dissertation to Euler with the following greeting: Hochedelgeborener Herr, hochgelehrter und hochberühmter Herr Professor, besonders hoch zu ehrender Herr. I mean, I would like to be addressed maybe just once with one of these titles. Kant gives Euler the whole treatment, and Euler does not respond at all. And not only does Euler not respond, it actually gets worse. 1750, he publishes his Réflexions sur l'espace et le temps in the Histoire de l'Académie Royale. So, it's ex cathedra. And it contains a blistering rejection of the position Kant had argued for. So not only will he answer the letter, he then publishes an article saying anyone who thinks something like this is obviously a fool. In that paper, he rejects out of hand the idea that absolute motion and absolute position are unreal, which is a thesis advanced on the very first pages of Kant's dissertation. And, that could have been the end of it. But when we look more closely, we see that Kant, in fact, never gave up. And I would go so far as to say that, at least as far as Kant's space-time theory is concerned, really, it's an ongoing effort on his part to satisfy Euler, and in fact, to satisfy Frederick the Great, to try and get into where the action is actually happening in Europe, which is where Euler and Lagrange are doing their work. And that theory that he develops is, in fact, the source of the light cone. In fact, it's the theory of the flat light cone, because it contains both the metrical and the causal components, with the one difference, of course, that the definition of simultaneity uses instantaneous causality. So from our point of view, Kant's theory of time is, on the one hand, on the mathematical side, a relative theory of time, not a relationalist theory of time, but a relative theory of time. Duration and simultaneity are intrinsic features of the manifold, independent of position or state of motion. So time has a metric, but it has no origin. And he also assumes with Leibniz that the structure in question, precisely because it's relational, must be ideal. Now, that's not going to be something that I'm going to talk about very much today. So we see explicitly this theory of time being stated at B67 of the Transcendental Aesthetic. The time which antecedes the consciousness of these presentations in experience already contains relations of before and after, das Nacheinandersein, the simultaneous, and of that which is simultaneous with the Nacheinandersein, the perdurant. So these are structural characteristics, right? Linear order, ubiquity, simultaneity, duration. But time has other very important features, not the least of which, of course, is Sukzession, or flow, or passage. And succession and flow is what is going to be explicated in terms of causal relations, above all the causal relation of efficient causality, where cause is prior to the effect, although of course that's not going to hold for the type of causality involved in communication, or bicausality, where at least in Kant's theory, the causal action goes in both directions and does so instantaneously. So I'm going to begin with the metrical part, and then in the second part of this talk, I'm going to turn and talk more about the causal structures that get connected to the affine geometry of the pheronomy in order to position Kant's theory against special relativity. And I'll say a few words in conclusion about EPR and a little bit about early phenomenology of time in Göttingen. All right, so the pheronomy presents a construction of the affine geometry of neo-Newtonian space-time. The mathematics, as I've already suggested, is taken from Euler's analytical mechanics. And the notion of an affine transformation, in fact, the term itself is also taken from Euler, although Kant does not use that word. So we can assume, I think, with a fairly high degree of confidence that the theory that he advances was understood in the terms that I'm about to explain to you in Berlin and Göttingen up to and through the work of Helmholtz and Klein. And in fact, you know, if you're wondering, I mean, Einstein himself occasionally uses the word pheronomy. Whether or not that means he was aware of Kant's work, I really can't say. On the other hand, he seems to have read vast amounts of Kant when he was already a teenager. The pheronomy is the first section of the metaphysical foundations. It's the part of the metaphysical foundations where the quantification of speed is going to be explained, and speed is going to be quantified in terms of two properties that it has. Of course, velocity, the rate at which you are moving through space, and direction. And direction is quantified in terms of pi, and speed is going to be quantified in terms of c over st. The principle of the pheronomy: every motion as an object of possible experience can be viewed arbitrarily as a motion of the body in space, or as rest of the body and instead motion of the space in the opposite direction. And this is, in fact, as we're going to see, is actually an output of Euler's proof. Euler is going to show us that the laws of motion are going to be the same in all inertial moving frames, and so you can pick your frame at will. And then the Lehrsatz, I think it's the Lehrsatz, right? The proposition of the pheronomy: the composition of two motions of one and the same point can only be thought of in such a way that one of them is represented in absolute space and the other one is ascribed to the motion of a relative space. So instead of representing a motion with respect to a frame that I consider to be at rest, I hold the point fixed and imagine the frame moving with an equal but opposite velocity, and I now assert that's one and the same state of affairs. They're indiscernible, therefore they're identical. The part of the proof that interests us most is the proof of the third additive law, because that's the one actually which, from our point of view, includes the other two as a special case, which is the problem of combining non-collinear velocities. So here's the diagram, which is actually taken from the original publication of the Metaphysical Foundations. The task is to figure out the sum of the velocities represented by AB and AC. And of course, what we want as our result is going to be AD. And we now apply the proposition of the pheronomy to say, well, this AC constructed in a frame that is moving to the left of our diagram with a velocity equal and opposite to AB is the thing we're looking for. We want to know what AC looks like in a frame that is moving to the left with the inverse velocity of AB, and we want to show that in fact AC will look like AD from the point of view of that frame. And that frame, of course, could be Galileo's boat, and later on, of course, it could be an Einsteinian train car. So that's how Kant approaches the problem of figuring out the sum of two motions. You construct the one in a frame moving with a speed equal and opposite to the magnitude of the second velocity that you wish to add. It's pretty clear that the proof itself, or the proof method, is borrowed from the Analytical Mechanics, Chapter 1 on motion in general. If you recall, Kant actually says at a certain point that our theory of time explains as much a priori knowledge as we have in the general theory of motion. Well, I think it's pretty obvious that it's the on motion of general that he's referring to. Here is section 77 of that. When the space from which the relative motion is determined is either absolutely at rest or moving uniformly, then the given laws prevail. That is to say, a statement of what we would today call Galilean relativity. And then Euler turns to the mathematical problem, which is to determine how you transform the coordinates of the rest frame into the coordinates of an inertially moving frame, and then to demonstrate to you that any inertial motion in the rest frame is also going to be a rectilinear and uniform motion in the inertial frame. And if we can now show that this property of rectilinearity and uniformity is preserved as we move from frame to frame, then we will have mathematically justified the principle of relativity with which we began. So the proof that Kant borrows is the proof in Euler where he's actually deducing for us the exact sign law that we call the Galilean transformation. And he's going to show you that when you transform coordinates following the Galilean transformation laws as Euler is articulating them here, you are going to get a family of motions in the inertial frame, all of which satisfy the laws of motion. So the output of Euler's proof is going to be the principle of relativity and the transformation that is associated with what we call Galilean relativity. So what he wants to do is not to construct the sum of two motions. On the contrary, he wants to know if I have a motion like AL in absolute space, and I've got some frame that's moving with velocity AM, he wants to know what does AL look like in the frame moving with speed AM. So he's going to subtract AM from AL to get AN. And you can now easily see that you could also use this proof running in the opposite direction, assuming relativity as one of your premises, and then deducing the kinematic parallelogram law that follows. That is to say, from the fact that AL minus AM equals AN, you could say invert the proof and do it in such a way that we get the sum of AN and AM, which is going to be AL. So this demonstration, says Euler, is of great practical utility to us because it allows us to transform relative motions into other uniform ones in which the laws will be observed and of which one can pick the most convenient. So this technique of transforming coordinates following Galilean transformations is of great use to us because it allows us to manipulate the description of a system to make it more easy to handle mathematically. So Euler derives the principle of relativity. He actually justifies it. And it's important to remember there's only one principle of relativity, right? Principle of relativity just says the laws of motion are the same in any uniformly moving frame. Kant does not derive the principle of relativity. He posits it. It's the output of Euler's proof. It's an input for Kant's proof. He posits a priori that the motion of a point in a rest space is identical with the point being held motionless while the frame moves with inverse speed, and then runs Euler's subtractive proof backwards. The structure you get at the end, if you correlate it with the law of causality of the second analogy of experience, instantly generates both of Euler's laws of inertia. And again, it's very hard for me to believe that that was not something that Kant had planned in from the very beginning. That's what these analogies were always there to do in the Critique of Pure Reason. So he constructs the sum of two motions by sketching the first in a relative frame and then looking at that from the point of view of the absolute frame. Now, since the mathematical description can be transformed in such a way while the laws still apply, we can use any frame we like to describe the system that interests us. But nevertheless, for Euler, only one frame is truly at rest. He is, in fact, a Newtonian, and he becomes even more strongly a Newtonian, as we saw by the time of 1750 when he publishes the Réflexions. Kant, on the other hand, is doing something quite different. It's mathematically less sophisticated, but from the point of view of the philosophy of science, perhaps more interesting. He's going to say the two ways of describing the system are just two different ways of describing the system. And now, applying this Leibnizian reasoning that I was referring to earlier, he's going to conclude, like many people in this tradition, you should just get rid of this notion of the background rest space. You don't need it. And the result of that is that you end up with a theory with the same physical content, which, however, no longer contains the notion of absolute rest or of absolute velocity. Okay, so having said that, I'm now going to turn to the causal part of Kant's theory, what Kant calls the time determination by means of dynamic categories. And of course, we know what those look like. We've got the second analogy, the principle of temporal sequence according to the law of causality. All alterations occur in accordance with the law of connection of cause and effect. And communication, the third analogy, the principle of simultaneity according to the law of action and reaction. All substances, insofar as they can be perceived in space as simultaneous, stand in relations of interaction at a distance. It's important to notice that the analogies actually are analogies. They are analogies between relata. The relata of two successive moments are analogized by the relata of a causal relation. The relata of two simultaneous moments are analogized as the relata of a bicausal connection. So the analogies are analogies in the strictest sense of the word. They're root analogies. The fundamental physical concepts of the critique of Kant's entire system, which of course are the schemata, and the schemata themselves, they said, are analogies because they put in connection to relata. The schema of cause is the real upon which something else always follows. It therefore consists in the succession of the manifold insofar as the succession is subject to a rule. And here's the root concept for communication or action and reaction. Its schema is interactive causality according to a general rule. So following remarks of Lambert on similar topics, we could say that the property of one after the other, nacheinander, while it's a mere order property, remember the mathematical part of the theory, when conceptualized in these modal logical terms, in terms of a modal logical if-then, becomes a concept of time in which the moments successively necessitate one another, which Lambert explicitly compares to clock cycles. So when you take the mathematical timeline and then you say, well, there's a property of successivity, and now you model the property of successivity by hooking up successive parts of the timeline by means of a causal relation of the type that I showed you on the first few slides of today's talk. So the general pattern is you take an aspect of time structure, succession, simultaneity, you attach a modal logical inference form to it, and by doing this, you causally determine time, and you thereby also causally determine space-time, and I'll show you why in just one second. So here's architecturally what's going on here. On the leftmost column, we have general logic, which are simply laws of thought. Then these general logical functions give rise to metaphysical concepts in which we simply replace the, you might say, propositional elements of the logical notions by means of variables that represent things. We get modal logical categories. The modal logical categories then have, you might say, a dual image, which is some aspect of temporal structure. So I've only done it for 3 here. I've done this for the entire category system. But obviously we're just talking about time and causality today. Substance property gets associated with perdurance, cause effect with succession, communication with simultaneity. The schema is simply the analogy that results from combining the two concepts that came right before. And the principle is just what you get by projecting that schema along the timeline and onto space and its material contents. So now when we extend that into the metaphysical foundations in the 19th century, I left out here the column where I actually put out all the laws of the metaphysical foundations. These principles eventually translate into principles such as conservation of mass, principle of local action, the Nahwirkungsprinzip, and the strong principle of action and reaction, the Wechselwirkungsprinzip. The only one you can see that survives is, of course, the light.cone. So we go all the way here from if then, cause effect, succession, efficient causality, second analogy of experience, which then becomes the principle of local action, and finally the light.cone or locality. But for that very reason, as Einstein himself highlights, both of the other two principles, conservation of mass and the Wechselwirkungsprinzip, action at a distance, are now no longer possible after 1905. Now, all you need to do to get this light.cone structure in Kant is to begin with the schema of time, and then you apply the second analogy to that line, and you get the notion of a timeline whose moments causally necessitate their successors. And now you already know from the construction of the pheronomy that if I'm standing still right here and time is just going by, well, everything that's in front of me standing right where I am, everything in front of me in time, if I just stay where I am, is causally determined by the second analogy. And now, since I know from the pheronomy's construction, I mean, there's different ways you can do it, but this is the fastest way of doing it. Since I know from the pheronomy's construction that any inertial path that I might have gone on, instead of just staying where I am, is also a rest state viewed from an appropriate frame, it now follows, of course, that anywhere I can get by means of an inertial path from my current space-time situation also falls under the scope of the second analogy, which means that all future events anywhere in space are in fact already causally determined simply by combining the second analogy with the phoronomical construction. All right, so I'll just skip that over because I just did that. The key point is that's not going to be the case for the simultaneous moments. The simultaneous moments are outside the scope of the second analogy. And the reason is, using the method I just used, as I said, there's other ways you could get there within the Kantian system. But using the method I just used, you can see the law only governs events that I can get to over some finite interval of time, right? And so successivity itself only manifests itself over some finite interval of time. So there's no way from the second analogy and the phoronomic construction of getting the causal determination of the plane of simultaneity. So the plane of simultaneity simply lies outside the scope of this law. And as we all know, Kant was aware of this already when he wrote the inaugural dissertation, because he said something that I'd already referred to on my first slides, that you don't get simultaneity simply by negating successivity. So, given that my present space-time situation is causally influenceable by all past events and can causally influence all future events, but is nevertheless causally disconnected from all simultaneous events, I cannot exchange information in any way with these other parts of the universe. You might say they are, at least for the moment, like behind an event horizon, unless I introduce some kind of a supplementary principle. And of course, that's what the third analogy is there for, and that's what the corresponding principles in the metaphysical foundations are there for as well. So the category of communication, Gemeinschaft, attaches to simultaneity to generate a law that asserts that there are such causal interactions, and thereby completes the causal determination of Kantian space-time. That's really, from my point of view, what the transcendental aesthetic and the transcendental analytic are describing. That and nothing more. So what has Kant done relative to his predecessor? Well, I already mentioned this before, that he's plugged in bicausal connections between the possible coexistences, which in Leibniz's theory were causally disconnected from one another. Knowing something about one moment one event didn't tell you anything about the status of some other simultaneous event. So Kant puts in bicausal connections to anchor simultaneity. And Einstein is now going to come in there and he's going to snip those links back out, restoring locality, though, of course, the resulting theory is not Leibniz's. It's, well, one of the most important theories, obviously, in the history of human thought. The fact that there's an internal connection between these two kinematic theories was already suggested by Robert Poulter in 1972, right? And Kant's and Einstein's derivation of the kinematic parallelogram law follow a very, very similar pattern. So the inputs to both proofs are some definition of time structure. In Kant, that would be B67 of the transcendental aesthetic. In Einstein, it's an explicitly implemented local theory of simultaneity. I say local because it employs actions which take a finite amount of time to disseminate. Secondly, a rest space, ruhiger Raum or ruhiges System, a relative space, the relativity principle, and I insist once again, there's only one relativity principle, and it's the same one in both cases. And one then simply constructs a motion in the relative frame by transforming its representation in the rest frame via the coordinate transformations that are consistent with your simultaneity criterion. And that's how you figure out what the kinematic parallelogram law looks like in your space-time. So you get a similar parallelogram law, except that the triangle of the Ferronomy is no longer Euclidean as it was in Kant. It's now hyperbolic. So the kinematic geometry is slightly altered, but the application of the causal law is essentially unchanged, because the causal law, even in Kant, didn't get us coverage of that whole, the whole of simultaneity. So when we construct the causal law within a hyperbolic kinematics, we actually get the principle of locality. So here is a definition of locality taken from the work of Pierre Eberhard, who works in quantum entanglement at Livermore Labs. He's not a Kant scholar, to the best of my knowledge, has no interest in any of the topics. Well, I shouldn't say that, maybe he is, but it's not an area of his research. And here's his definition of locality. Locality, the principle of local causes, is derived from the principle of causality, which requires that in time the cause must precede the effect, that is to say, our second analogy, and from the principle of relativity, which implies that all reference frames are equivalent. You combine those two laws and you get what we mean by locality. And really, to drive home the point, that's exactly what you find when you go to the metaphysical foundations, right? Because the second law of mechanics, I hope it's the second and not the third, I always get confused. The second law of mechanics restricts the possible causes of a physical event to ones that are in the past. You already have that from the Critique of Pure Reason, so they're in the past, but you actually don't have an explicit statement that they've got to be in space. Since in the metaphysical foundations, we're talking about matter defined as the movable in space, now the possible causes of a physical event have been constrained to things that are in the past and in space, and that is in fact the flat rearward light cone. So when I say that this is the flat light cone, I don't mean this in any way metaphorically, and I would add to that, by the way, as a corollary, that if you think that this is doing something else, then you really need to show that at the level of the text, because these connections are systematic, wide-reaching, and they cut through the entire Kantian corpus. All right, the principle of communication, the third analogy, is unfortunately not compatible with our new non-flat locality, second analogy. And the reasons for that are quite well understood, so I'm just going to go through them fairly quickly. We no longer have a single slice of simultaneity corresponding to moments which are neither before nor after. Go to my first slides if you want. We now have a space-like region of such points. And now suppose hypothetically that someone in my FTL separated light cone wing, as one says, in the space-like region can communicate with me instantaneously. Well, it follows from SR that there's got to be at least two frames, in one of which the causal connection goes forward from me to her, but then forcibly there's going to be another frame in which that same relationship is going forward from her to me. But one of those two is going to violate the causal law. So the effect of changing the geometry of the triangle in the pheronomy from Euclidean to hyperbolic is to render the second and third analogies incompatible with one another. And of course, Einstein, like most reasonable people, took it to be the causal law that was going to continue to be valid. That's, in essence, saying locality holds. And if locality holds, then certain other things can't hold. And in particular, there can't be actions at a distance. And if you've read a lot of Einstein, you know that's a point that he likes to make a lot when talking about other people's work is, you know, whether or not locality is in fact being preserved. So in EPR, effectively, the argument is we're not going to give up on locality. And as a result, of course, the presence of these pseudo actions at a distance, which we call quantum entanglement, is a demonstration of the fact that QM must be incorrect. It's not going to be the causal law and locality, which is going to be sacrificed. And I think it's very interesting as a result where we've ended up. Because of course, as we now know, Einstein was wrong about this, but wrong, as is, you know, often the case with Einstein, wrong in a deeply interesting way. So FTL communication is partially possible, which seems to imply that we either have to abandon the law of causality, and with it, the causal asymmetry of time, or we have to become anti-realists. Now, there's some more interesting things going on here, and I'm just going to touch on them. This is something you might think about for further research. And again, as I said before, right, the point of this is not to say, oh, Einstein took all these ideas from Kant. What interests us here is the core causal theory of time and what it has to tell us today, because it still has a lot to tell us, I think, about EPR and entanglement. So if you look at the third analogy, you see that the empirical marker of simultaneity, this is, you might say, a property of the schema. So it's a second order property of these quite complex definitions, is symmetry. Whereas the empirical marker of successivity is asymmetry. So we have this order indifference and order dependence. Now what we see in EPR, and they've motivated remarks of Dirac's from 1930, where Dirac explicitly associates non-commutativity with necessary successivity. So if measurement operators can't commute, says Dirac, what that means is you can only know their values successively. Conversely, operators that can commute, well, in principle, you could know their values simultaneously. So in fact, locality is here being connected with properties of our measurement operators, and the properties of the measurement operators that play a role both in the EPR argument, but their ancestors play that same role in the second and third analogy, is the order in which you can come to know things and whether or not you can come to know them in an arbitrary order or in only one order or even conceivably at the same time. So what EPR are doing in some way is exploiting what Einstein had called these ghostly actions at a distance to demonstrate to you, and this is the central contradiction of EPR, that two events which must be successive according to QM can nevertheless be simultaneous. And that's the core absurdity which drives the EPR argument. So you see that this incompatibility between second and third analogy and of the symmetry and asymmetry of markers that are associated with those concepts is still playing a role in EPR itself. Where does that then leave us? So here's Eberhard again in this classic paper. The conflict with locality arises when the question is asked, how does nature do it? According to the Copenhagen interpretation, quantum theory is not supposed to provide a description of the physical process, but only a set of rules. The only causality that counts concerns the causal action one observer can have on another one. In other words, there is no contradiction between entanglement and locality if we become Copenhagen physicists and we effectively deny that we are describing a mind-independent objective reality. And Eberhard's rather transient assessment of this position, the inconvenience of this option is that the desire to understand how nature works has been historically a powerful motivation for scientific research. So if you want to be a realist, you can reject that. But if you reject that, then you are back in the boat of saying that locality has in fact been violated here. All right, let me say a few things here that I mentioned earlier about the state of play today, right? Because this lecture should not really have to be given in 2020, right? Its content would not have surprised anyone at the Institute of Mathematics in Göttingen in 1910. And if you read carefully through Weil's work from the 1910s and the 1920s, you can tell that he is thinking about the theory of relativity, and in fact, the theory of general relativity, and even gauge theory, his early works in gauge theory, from this point of view. So when I say it wouldn't have surprised anyone in Göttingen in 1910, and Göttingen is where Thomas Sturm and I first met and became friends. So there is, you might say a topic of long standing, and I'm very happy to be able to bring this up at this conference, right? Because who is there at that institute? Well, Hilbert, of course, Noeta, Minkowski, Einstein, but also Husserl and Hermann and Helena Weil. And of course, this is exactly the period during which Husserl begins to work on the phenomenology of time consciousness. So here's a wonderful quote from Weil's Raumzeit Materie, where you can see this really coming out, right? The deep mystery of temporal consciousness, of the temporal progress of the world, of becoming, has been recognized by the human mind since it awoke into freedom. In ihr liegt eines jener letzten metaphysischen Probleme, dessen Klärung und Lösung Philosophie durch die ganze Breite ihrer Geschichte unablässig gerungen hat. There is some kind of a deep connection between the notion of intuition, the choice of an inertial frame, and the choice of a gauge. And I haven't been able to figure out exactly what it is, but I think that Weil knew. And I think the good news is there's a lot of really interesting work to be done here for the future if people would just start reading Kant in a serious way. Thank you for your attention.